So, what really makes us alive? Let's find out. Why doesn't the scooter catch a fever? What makes us different from a scooter or a rock? What really makes us us? Is it just our body or is it something more? What is you? Is your arm part of you? What if I removed it? Would it still be part of you? What about the food you had for dinner? It wasn't you yesterday, but soon parts of it will be absorbed into your cell, become the molecules that make up you. Hi friends, so in this video we are exploring questions that define what it means to be alive, from molecules that spark life on a chaotic earth to viruses that blur the line between living and non-living to artificial intelligence, lab-grown organs that challenges the very concept of life itself. We will even deep dive into mysteries of quantum mechanics and how randomness might hold the key to life itself. So what really makes us alive? Let's find out. But for me, this started with a much simpler question, a question that I asked my dad when I was a 10-year-old kid. When I was a 10-year-old, I was playing outside in the rain. My father called me in and said, "Come inside, you will catch fever." That made sense, but my 10-year-old brain asked him something that stayed with me forever. I pointed to the scooter that was outside in the rain and asked him, "Why doesn't the scooter catch a fever?" My father didn't have any answer, and honestly, neither did I. But that simple question stayed with me forever and sparked something in me. What makes us different from a scooter or a rock? What makes us alive? That question stayed with me, and as I grew older, I started asking bigger questions. What really makes us us? Is it just our body, or is it something more? To answer this, to understand this better, let's start asking a different question. uh, what is you? Is your arm part of you? I'm guessing you would say yes, but what if I removed it? Would it still be part of you? Probably no. Then what about the oxygen you are breathing right now? Is that part of you? Without it you wouldn't survive. So in a way it is as much you as your arm is. And what about the food you had for dinner? It wasn't you yesterday, but soon parts of it will be absorbed into your cell, become the molecules that make up you. So, where do we draw the line? The truth is, the edges of you are far more blurred than they seem. To find the answer to what makes us alive, we need to go back in time, billions of years ago, to a very different Earth. So, back then, Earth was a chaos, a stormy world where particles collided, broke apart, recombined. Imagine a giant soup of chemicals bubbling in a pot. That's what Earth looked like. In this chaos, tiny molecules bumped into each other. Most of the time, nothing happened, but once in a while, two molecules would stick to form something new. These bonds were fragile and often broke apart, but sometimes they held it on long enough to attract more molecules, setting off a chain reaction. In this turbulent soup of chemicals, molecules were constantly colliding. Most encounters led nowhere. A bump here, a scatter there, but occasionally, by pure chance, molecules would bond, creating something new. These early bonds weren't intentional or designed, they were simply the result of right conditions coming right together. Over time, certain molecules become more complex, capable of interacting with environment in unique ways. Some could catalyze reactions, helping other molecules come faster together. The ability to act as a catalyst was a game changer. Imagine one of these molecules facilitating the creation of another molecule similar to itself. It wasn't a perfect copy, but it shared enough of the original structure to perform the same function. This was the earliest form of replication, a molecule indirectly creating more of its kind by guiding chemical reactions. As the reaction continued, replication became more efficient. Molecules that were better at catalyzing their own production had an edge. This wasn't conscious or deliberate, it was simply a matter of probabilities. The more effective a molecule was at guiding replication, the more likely it was to persist in the chaotic soup. This wasn't evolution as we think of it. It was just a random process where stability led to survival. A survival led to more chances of replication. Think of it like seed scattered in the wind. Most fallen on barren ground and disappear, but a few land in fertile soil and grow. Over time, only those successful seeds remain. This is what we call survivorship bias. We notice the survivors because the failures didn't stick around. Here's another example of survivorship bias. When we walk into a coffee shop, you might see photos of happy customers and think the shop is amazing, but you are not seeing the unhappy customers who never came back. That's survivorship bias, focusing only on the of successes while ignoring all the failures. The same bias applies to life. The molecules that could replicate are the ones that survived. The ones that could not survive were simply lost to history. Eventually, more sophisticated molecules emerged, like RNA. The molecules acted as both instructions and tools for replication. RNA could store informations and catalyze reactions, making it a perfect candidate for life's earliest building blocks. A perfect survival of the fittest molecule that wins the statistical game, an outcome saved by survivorship bias, where only the successful remain for us to observe. This process of copying introduced tiny changes over time. Molecules that could replicate faster or use less energy had an advantage. This wasn't evolution by design, it was a natural selection at its most basic level. Only the molecules that survived were left to copy themselves. Once molecules began replicating, tiny copying errors led to variations. Most didn't matter, but some helped molecules survive better. Over time, these changes built up, leading to the incredible diversity of life we see today. This is evolution in action. The successful ones thrived while the others disappeared. Over millions of years, these small changes added up, leading to incredible variety of life we see today. For example, a giraffe's long neck likely started as a small advantage, helping it to reach higher branches. Over time, this small difference make a defining trait passed down through generations. This process of small changes building up is how all life evolved from simple molecules into complex world we know today. But evolution does not just shape life diversity, it also forces us to rethink what it truly means to be alive. For example, not everything fits neatly into the category of life. Some things blur the line between living and non living. So, where exactly do we draw the line? To explore this question, let's take a closer look at viruses. They cannot move, eat, or reproduce on their own, but when they invade a host, they hijack its body and its machinery to make copies of themselves. So, viruses are alive, or so are viruses alive, or are they just molecules reacting to their surroundings? And what about AI? Machines don't breathe, eat, reproduce like us, but they can learn and adapt. Some AI bots today can already do tasks that feels remarkably human, like writing essays, diagnosing diseases, and creating art. Soon we might have AGI, artificial general intelligence, that can perform any task a human can do. But here's something even stranger. Scientists are working on computers powered by human brain cells, often called as organoid intelligence. Imagine a system that combines the adaptability of human intelligence with the speed of machines. Could that be considered alive? Now let's consider artificial organs. Today, science in creating 3D labs, lab-grown tissues, and 3D printed organs, from kidney to heart, researchers are pushing the boundaries of biology. But this raises a deeper question: if you replace every organ in the human body one at a time, are you still the same person? This is the essence of Ship of Theseus paradox. If you replace every plank of a ship, is it still the same ship? Let me explain this better. Let there be a ship called Theseus, and you replace each part of this ship one by one. Also, if you create another ship using the replaced parts, uh, does the new ship created using the replaced part call the Ship of Theseus? Or the old one, which was slowly replaced one by one, is Ship of Theseus? This explains how blurred the definitions are, the namings are. Similarly, if you replace every organ in our body, what defines you? Is it your body, your consciousness, or something else entirely? Perhaps consciousness is less unique than we believe, just a byproduct of patterns and reactions, not a mystical essence. Whether it's a virus, a machine, or even a human body made of artificial parts, it all just the results of patterns and of chemical and physical reactions. uh, to understand this better, I would recommend a very good movie. There is an Indian movie called Ship of Theseus that explores these questions beautifully, using organ transplants to ask deeper questions about identity, purpose, and what makes us who we are. It is available on YouTube. I will share the link on description below. Today, life feels purposeful. It feels like we are here for a reason, but that's just an illusion. Think about a car engine. By itself, metal does not move, rubber does not decide where to go. But when all the parts come together in a right way, the engine runs. Life works the same way. It is just molecules arranged in a way that allows them to move, react, and persist. Take food for example. It is our fuel. Just like diesel powers an engine, when you eat, your body breaks down the food into smaller molecules, releasing energy to keep you going. Similarly, an engine burns diesel to release energy and drive the car forward. So, how can you differentiate between a human and a car? And what about stimuli? A car does not move on its own, it needs someone to turn the key, press the accelerator, steer the wheel. Humans are no different. Our actions are driven by external stimuli, light, sound, temperature, and even the presence of other people. Just as the engine does not think about where to go, we don't consciously control every reaction or decision. In both cases, it's not about the purpose or intention, it's about system responding to inputs. The car systems are mechanicals while ours are biological. But at the core, they operate on the same principle of energy transfer, reaction, and persistence. Now, moving ahead to the next part. From molecules and cells to viruses and AI, we have explored life as we know it. But what if the answer lies even deeper at a quantum level? At the quantum level, particles don't behave the way we expect. They can be in multiple places at once or even exist and non exist at the same time. But here's the strange part, these particles only decide their state when we observe them. There is a famous double slit experiment related to this, you can check out about it. To explain it simply, it is like flipping a coin in the air. Until it lands, it's neither head nor tails. Life might not be different. It is also random, but randomness shaped over time into patterns. But this is just the beginning. We will explore this connection between quantum mechanics and life more deeply in future videos. So you can subscribe to my channel. Now let's conclude all this. From chaotic molecules to viruses, AI, and artificial organs, the line between living and non-living keeps blurring. Consciousness may not be spatial, it's just the result of chemical and physical reactions. No soul, no deeper meaning, just the organized dance of atoms and energy. So, what do you think truly defines life? Share your thoughts in the comment section, and curious to learn more? Subscribe to my channel and join us on this journey to unravel the greatest mysteries of life and the universe.